That last unit had a lot of ideas, learning how to transform problems that didn't appear to be standard form linear programs into standard form linear programs. We'll use some of those ideas to look at the regression problems we solved a few modules ago and change from the squared error criterion to some other criterion. This slide is drawn from the regression module, as well as some new ideas at the bottom. In regression, there were several ways to quantify the amount of mismatch over the entire data set. The square root of the sum of the squares, the sum of the absolute values, or maybe even just the maximum entry. In the regression module, we used the squared criterion, motivated for a few reasons. But we also stated that in the linear programming module, we'd see how to optimize the function choice based on the other criteria. And that's what we'll do right now in this unit. For notational simplicity, let's define some new norms and use additional notation to differentiate among them. If I have a vector e, e1 through en, the 2 norm, notice the subscript 2, will be the familiar norm that we've used all along, the square root of the sum of the squares of the entries. This is the Euclidean norm. We'll also use something called the 1 norm, and that's the sum of the absolute value of the entries, as well as the infinity norm, and that's just the largest entry. So now with just a norm symbol and a subscript, 2, 1, or infinity, I can get those formulas above without all the notation. Of course, you do have to remember what each of these means. 2 means square root of the sum of the squares, 1 means sum of the absolute values, and infinity means maximum. But with that, the notation is a lot cleaner. Let's remember what the least squares problem was. It was the problem of minimizing the norm of ax minus b. The setup is a matrix that's n by m, and a vector b, which is n by 1, and we want to, over all choices of m by 1 vectors x, minimize the mismatch between ax and b, and measure that mismatch in terms of a norm. Minimize over x the norm of ax minus b. Least squares addressed the 2 norm, the square root of the sum of the squares. It used calculus and derivatives to determine the conditions for optimality, and that resulted in the normal equations, a square system of linear equations that always has a solution at the optimal point. Linear programming can address these other 2 norms, the 1 norm, the sum of the absolute value of the entries, and the infinity norm, the maximum of the absolute value of the entries. Let's see how that goes. Let's talk about the infinity norm, the maximum of the absolute value of the entries. So the setup is the same, matrix A and vector B. To match things up with some of the derivations we've done before, let's define vectors Ci, these are m by 1, such that transposed and stacked, they constitute the array A. So the C1 transpose is really the first row of A. That means, of course, that the ith entry of ax minus b is simply the ith entry of ax, which is Ci transpose x, minus the ith entry of b, which is bi. And that'll be useful as we work through this infinity norm, which involves the maximum over all the entries. Using this notation, the minimization over x of the infinity norm of ax minus b is the minimization over x again of the largest entry of ax minus b in absolute value, and we know that each entry of ax minus b is of the form Ci transpose x minus bi. So the absolute value gets the absolute value of the entries, and the max over all the entries gives us the infinity norm. And this is subject to no additional constraints. That is the problem. Find the best x to make ax minus b as small as possible in the infinity norm sense. From the previous unit, we know how to deal with the maximization of the absolute value of a collection of numbers. We introduce another variable t and do a minimization over that variable, subject to the constraint that t is larger than the number as well as larger than its negative. This is exactly the step we did before. For every value of x, the 2 bracketed expressions are exactly the same. Outside, there's a minimization over x, and in this case, no additional constraints. As in the previous unit, this is a joint minimization. Minimize over x and t jointly, the cost function, which is t, subject to all the constraints. The constraints are simply of the form Ci transpose x minus t is less than or equal to b, as well as negative Ci transpose x minus t is less than or equal to negative bi. And there they all are listed. Let's now remember that C1 transpose stacked above C2 transpose stacked above Cn transpose is the array A, and B1 down to Bn is the vector B. This can be written much more concisely as minimize over x and t, subject to the linear inequality constraints listed there. The boldface 1n is a vector of 1s of dimension n by 1. This is very clean. We've now cast the norm minimization of ax minus b in the infinity norm as a linear program with m plus 1 decision variables and 2n linear inequality constraints. How about the one norm minimization? The setup is the same, and again we'll use the notation where the Ci transpose are rows of A. Now we're interested in minimizing the one norm. The one norm is the sum of the absolute values of the entries. Remember that each entry of ax minus b is of the form Ci transpose x minus bi. So there is the one norm of ax minus b. As we learned in the previous unit, the summation of absolute values can be written as a minimization. The bracketed term is the summation of the absolute values for any value of x. Find the smallest summation of real numbers t such that each real number ti is greater than Ci transpose x minus bi as well as the negative. Now I'm going to leave one step for you to verify yourself, and finally we'll end up with this very clean expression where we have a linear objective involving the sum of the t's as well as 2n linear constraints. The only thing that's changed from the infinity norm is now the t is a vector, and the vector of 1s has been replaced by identity matrices. Reiterating though, we've now cast the one norm minimization of ax minus b as a linear programming problem involving m plus n decision variables and 2n linear inequality constraints. You're going to program both of these up in the lab assignment and compare them to least squares. They achieve different objectives in terms of what they minimize, but all are computationally feasible even at large scale.